This is 10.1. We're going to be dealing with exponents in this module. So if I had 4 plus 4 plus 4, I can rewrite that using multiplication as 3 copies of 4. But what if I had well, that'll be good enough. So this becomes 3 times 4. And this becomes 3 times 4. And that would be 6 copies of 4. Okay, now I'm not teaching anything new. This is just a review. All right. Well, what if I had 4 times 4 times 4? That would be 4 to the third. Okay. But what if I had 4 times 4 times 4 and 4 times 4 times 4? So this is 4 to the third, and this is 4 to the third. So that's 4 to the third squared, right? So if we counted out all the 4's here, we have 3 there and 3 there for a total of 6. Or if we look at it in this form, 3 plus 3 is 6. So if we look at it in this form, how does the 2 affect the 3? We use multiplication, 4 to the 6th. So if you have a base to a power, and all of that is raised to a power, essentially we're saying we have 5 copies of this. So 3 to the 4th times 3 to the 4th times 3 to the 4th, 3 to the 4th, 3 to the 4th. And we add up all those 4's, and I get 3 to the 20th. So whenever you have a base and an exponent that is raised to an exponent, you multiply those exponents together. Okay. So in this problem, w to the 5th to the 3rd, that's like saying w to the 5th times w to the 5th times w to the 5th, which is w to the 15th. Okay. All right. Negative 2ab squared raised to the 5th. So I'm going to rewrite this with exponents on everything. Raise that to the 5th. So 5 is going to multiply by 2 and 1 and 1. So that gives me negative 2 to the 5th, a to the 5th, and b to the 10th. And this one I can actually figure out the answer. Negative 2 times negative 2 is 4, times negative 2 is negative 8, times negative 2 is 16, times negative 2 is negative 32, a to the 5th, b to the 10th. And notice, I put this one in parentheses because of the negative. Right? There's a difference between negative 2 to the 4th and the quantity negative 2 to the 4th. According to order of operations, we have to do exponents before we do subtraction. So this one is saying, what is 2 to the 4th? And that would be 16. And then take the opposite of that. So this would be negative 16. But this one is saying, what is the 4th power on the negative 2? And that would be negative 2 times negative 2 is 4, times negative 2 is 8, times negative 2 is 16. So it's really important when you have negative numbers raised to an exponent that you figure out should they go in the parentheses or not. So if we had another problem, negative 3 x squared y to the third, and we raised that to the fourth. So I'm going to put a 1 inside there, and then I'm going to multiply all of those by 4. But the negative has to be in parentheses. So negative 3 to the fourth, and then x to the 8th, and y to the 12th. And then negative 3 times negative 3 is 9, times negative 3 is negative 27, times negative 3 is 81. So 81 x to the 8th, y to the 12th. So if this power is even, the negative is going to go away. But if this power is odd, then the negative hangs around. Okay, do you want to see another one? Do you get that? Okay, we're good? All right. So here we just have a long string of multiplication. So we're going to multiply all the numbers together, and then we'll multiply all the y's together, and then all the w's together. So as far as the numbers go, 4 times 2 is 8, times 2 is 32. And then y to the fourth and y to the third makes y to the seventh. And then w squared times w is w to the third. Make sense? All right. Scientific notation. Sometimes we deal with numbers that are so big or so small, we just have lots and lots of zeros. And if I wrote down a number, how big is that number? It's kind of hard to see, so sometimes we count over and put a comma, and then we count over and put a comma, then we count over and put a comma, and then count over and put a comma, and then we count, okay, this is hundreds and thousands and millions and billions. So this is 1 trillion. And we can actually turn that into a number that's a little bit easier to understand. So right now, my decimal is here. And if I move that decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I would get 1.235 times 10 to the 12th. Okay? And what that means is I have a number that starts with a 1 and it has 12 digits after that before I hit the decimal. So to turn scientific notation into standard notation, because this is a positive 12, we would move to the right 12 digits. And it's just an easier way to deal with really, really large numbers or really, really small numbers. So this problem says, what is 2 times 10 to the negative 3? Well, that 3 is positive, so we need to move that number 3 units to the right, or that decimal 3 units to the right. So 2.0. I'm going to move this 1, 2, 3, and then I just fill all of those in with zeros. So 2 times 10 to the third is the same thing as 2,000. Okay, let's do another one. Let's say that's a 7. So 9 times 10 to the 7th. So I start with my 9.0, and I move it 1, 2, 3, 4, 4, 5, 6, 7. And then I fill that in with zeros. So this is 90 million. All right. Okay. So here, I have 3.2, and I'm going to move that 9 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then fill in zeros. And I'm going to multiply that by 2, and then 1, 2, 3, 4, 5, 6. So multiplying that out is going to be a pain, right? If we did that by hand, it's going to be messy. So there's actually an easier way to do it. If I had A times B, and I multiplied that by C times D, according to the rules of multiplication, I can commute those variables. I can move them around, right? A times B times C is the same thing as A times C times B. The order of multiplication doesn't matter. So if this is A times B times C times D, I could rearrange it so that it's A times C and then B times D. So up here, I just have a whole bunch of multiplications. Here's A, here's B, here's C, and here's D. So I'm going to rearrange it into AC times BD. So 3.2 times 2 times 10 to the 9th times 10 to the 6th. Okay. Well, what is 3.2 times 2? 6.4. So this piece is 6.4. Now, that piece might look a little frightening, but if I had x to the 9th times x to the 6th, that would just be 9x's times 6x's, and I just count them all up, it would be x to the 15th, right? So 10 to the 9th times 10 to the 6th is just 10 to the 15th. And I just multiplied those massive numbers together, and it was super, super easy. So that's another thing that scientific notation allows you to do. It's multiply or divide really massive numbers or really, really tiny numbers. All right, let's do another one of these. All right, I'm going to multiply these together. 4 times 2.1 is going to be 8.2. And then 10 to the 5th times 10 to the 6th is just 10 to the 11th. 5 plus 6. Okay. All right, write this in standard notation. So we're just going to move this decimal 1, 2, 3, 4. So 9.1460. Okay, what do we do here? Well, I need to multiply all of these by 4. So the first one is still negative 3x y to the third z squared. And the next one, don't forget that the negative has to go in parentheses. And then y to the 12th, z to the 12th. And then we focus in on this one. negative x squared times negative x squared times negative x squared times negative x squared is going to be positive x to the 8th. So negative 3x y to the 3rd z squared y squared z, or y to the 12th z to the 12th. And that leaves me with negative 3. Then count up my x's. I have 9. Count up my y's. I have 15. Count up my z's. I have 14. And that's it. Okay. Get to work.